Hi everyone, this is going to be lesson number 7 on the topic of structure, bonding and properties for GCSE Chemistry students. In this lesson we're going to be looking at the kinetic theory of matter. So let's take a look at the learning outcomes for this lesson. So once you've completed this teaching video, and if you're watching it on my website, once you've completed the various questions that will pop up at intervals throughout this video, together with the other learning activities on this lesson's page, you should be able to do the following things. So the kinetic theory of matter is a theory predicated upon the idea that matter is made up of particles, that the particles are in a constant state of motion, and that the particles behave like point masses which collide and move in accordance with Newton's laws of motion. Now, as we'll see, there are some simplifications being made in those assumptions, and there are some limitations of this model, but it's a very powerful model because it can be used to explain the physical properties of matter in its various states, solids, liquids, gases, and so on. So essentially, we need to describe the main features of the particle model and explain the distinction between physical changes and chemical changes with reference to the particle theory. Now, it's something that we've already looked at in previous lessons, the idea of physical changes and chemical changes, but we will be revisiting that. Obviously, we need to look at what the particle model has to say about the arrangements, the bonding between, and the motions of particles in solids, liquids, and gases. So we're going to be revisiting that as well. This is something that you will have come across from the very earliest stages of your science education, but hopefully we'll be able to develop those ideas a little bit further in this lesson. We also need to distinguish what happens when you provide heat energy to a substance and its temperature rises, or take away heat energy from a substance and its temperature falls, namely the difference between heating and cooling versus changes of state which happen at a constant temperature. So we're going to be looking at the concepts of specific heat capacity and specific latent heat as well. And we also need to then go on to talk about how do we calculate heat energy changes for objects which are increasing or decreasing temperature by means of the concept of specific heat capacity, and also heat energy changes involved in changes of state. So there's quite a lot to get through in this lesson. Now, as always, I have a number of students joining me via Zoom, many of whom have asked a number of very pertinent questions concerning these topics. I hope to answer many of those questions during the course of the recorded segment of this lesson, but for those of you who've asked questions that go beyond the GCSE level, I will be addressing those questions in the Q&A discussion that will follow, so please hold on for those. Now, if you're watching this as a recording, either on my website from within the GCSE Chemistry course or elsewhere, such as on YouTube, then please do send me your questions and I will answer those. If you are enrolled on this course, you can go to this lesson's page in the course navigation, and you can either type those questions into the live chat on that page, or alternatively you can use the private messaging function to send me your questions privately, in which case I'll typically respond with an answer within about 24 hours. If you're watching this elsewhere, such as on YouTube, then you can type your questions in the comments and I'll get back to you there as well. Okay, so let's make a start then. So I'm going to start with some very basic ideas, which hopefully you will have encountered before, and then build up from there. So in the early years of your science education, probably when you were somewhere between the ages of 9 and 11, you will have encountered particle diagrams, which in which you display the way that atoms and particles and molecules of substances are arranged in the solid state, in the liquid state, and in the gaseous state. So let's start with that. So in the solid state, particles are packed very closely together, they're almost touching, and they are moving vibrationally around average fixed positions in a regular repeating geometric pattern, which is often called a lattice or a crystal structure. So the particles are in motion, but they're in vibrational motion. And so in the solid state, the particles don't possess sufficient kinetic energy to overcome the forces of attraction between them and move translationally, that is to say, to move randomly past each other. They can only vibrate in these average fixed positions. And so this gives rise to some of the characteristic properties of solids. They're difficult to compress, for example. They will be resistant to deforming forces to some extent, or at least to a greater extent than liquids. Solids will tend to keep their shape, and the shape can change when you apply sufficient force, but typically they will keep a specific fixed shape in the absence of deforming forces. Now, in contrast, in the liquid state, or rather, before we get to the liquid state, when the concept of temperature is something that we're going to be visiting in this topic. As we'll see, temperature can be defined operationally by means of measurement as a degree of hotness or coldness on a chosen scale, or it can be defined more theoretically in terms of being a measure of the average kinetic energies of the particles of a substance. So, in a solid, the motion of the particles is vibratory. It's an oscillatory motion around average fixed positions. So if we take the idea of temperature as being a measure of the average kinetic energies of the particles of a substance, then as you raise the temperature of a solid, the particles will move more rapidly and will have a higher average kinetic energy. And so the particles in a solid are not free to move translationally, but they do vibrate. So, before we go on to looking at the liquid state then, let's quickly jot down a couple of very important definitions. So let's start with the idea of temperature here. We can define temperature in a very basic way as being a measure of hotness or coldness, but the actual more rigorous theoretical definition of temperature is it's an indirect way of measuring. It's a measure of the average kinetic energies of particles. So the higher the temperature, the higher the average kinetic energy. Now what this means is that on the microscopic scale, if you have an object and you raise its temperature, the total amount of kinetic energies of the particles will increase. Now there's a couple of very important other key terms that you need to be familiar with in terms of this area of chemistry and physics that we call thermodynamics. So temperature is a measure of the average kinetic energies of the particles. Now you might come across the term thermal energy. And this is the term used to describe an object or system. So when we use the term thermal energy, we're using that term in reference to the thermal energy of an object or a system of objects. So the thermal energy is the sum of the kinetic energies of the particles of that object or that system. Therefore, if you have a solid object, for example, and you raise its temperature, the average kinetic energies of the particles will increase, and therefore the sum of those kinetic energies, the thermal energy of the object, will increase. When you decrease the temperature of that object, the thermal energies of the kinetic energies of the particles on average will be lower, which means that the overall thermal energy of the object will be lower as well. The thermal energy of an object or system is the sum of the kinetic energies of the particles of that system. Now, this is distinct from internal energy. Internal energy. So the internal energy, again, refers to the internal energy of an object or a system. Now, the internal energy is the sum of the kinetic energies and potential energies of the particles that make up that system or object. So the internal energy of an object includes the thermal energy plus all of the potential energies of an object or a system. Now this term, potential energy, in general, potential energy is the energy due to arrangement or position. So particles in a solid, a liquid or a gas will have forces of attraction that operate when those particles are close together. So those forces of attraction hold these particles in place. The particles also have within them atoms which are chemically bonded together. If we're talking about molecular substances like water, those bonds themselves signify arrangements of atoms within those molecules, and there is a potential energy associated with those bonds. The atoms themselves have subatomic particles in their nuclei and electrons orbiting those nuclei in energy levels. All of those arrangements are also associated with a certain amount of potential energy. So the internal energy of an object or a system is the sum total of all of the kinetic energies of the particles of an object plus all of the potential energies of those particles of that object. So the internal energy includes the thermal energy plus the potential energies of those particles. Now, one final term, now we're going to be coming back to these definitions, but I think it's useful for us to note them down, is the term heat. Let me change back to the blue color here. So the term heat, sometimes people will use the term thermal energy interchangeably with the term heat, and they're not quite the same thing. Unfortunately, sometimes we'll also confuse the term heat with temperature. Again, they're not quite the same thing. Heat is the transfer of thermal energy from a higher temperature to a lower temperature. Object or system. So, heat is a transfer of energy. It's specifically a transfer of the internal energy, the component of the internal energy which is made up of the motions of the particles of an object. So when we have one end of an object which is at a higher temperature and the particles are moving more rapidly, the heat will be transferred. That thermal energy will be transferred to the cooler parts of the object until all of those parts of the object are at the same temperature. And we have achieved what we call thermal equilibrium. That transfer of thermal energy is referred to as heat. When we say we are heating an object, what we're doing is we're transferring thermal energy from a hotter object to that colder object and raising the temperature of the object that we're heating. Conversely, when we take away thermal energy from an object, we are cooling it, and we are transferring thermal energy away from that object to a cooler object or region or system. So that's what we mean by heat. It is the transfer of thermal energy. So these are very important terms. And we're going to be using these terms, and it's very important to draw the distinction between these. So let's move on to the liquid state now. Now, you'll notice that so far I'm using the idea of particles as though these particles are featureless spheres of material. Obviously, this is not the case for all substances, in fact, for any substance. Even noble gases. So if we look at noble gases in group 0, all of these are monatomic elements. They exist as individual atoms moving around. But those atoms themselves are not featureless solid spheres, as is being depicted here. They are, in fact, composed of mainly empty space, within which you have a small, dense, positively charged nucleus surrounded by clouds of moving electrons in energy levels. But then this model, this idea of particles as being these featureless spheres is even less applicable to molecules like water, for example. So molecular substances, simple molecular substances, are composed of groups of atoms chemically bonded together. So this is one of those PHET simulations that you can try for yourselves. I'll embed this on the lessons pages. So we can take a look at some molecules here, like water, for example. So water is composed of an oxygen atom chemically bonded to two hydrogen atoms. These are two covalent chemical bonds here. So here we see one of the hydrogens, here is another hydrogen, here is the oxygen atom in red, and these are the two single covalent bonds that link the oxygen atom to the hydrogen atom. Now what you're seeing here are the two non-bonding pairs of electrons around the oxygen atom. And so you see that if we choose to represent solid water like this, by means of a particle diagram like this, we're not taking into account the fact that in fact those water molecules are not featureless spheres. They have their own internal shape and geometry. And so the actual situation is much more complex because these bonds will move, they will bend, they will vibrate, they will rotate. All of these motions have an associated kinetic energy that contributes to the thermal energy of that water. And when these particles collide with each other, they don't actually collide as though they're featureless spheres that collide perfectly elastically. If you imagine another particle of water coming in and colliding with this one, obviously these bonds will move, they will vibrate, they will rotate as a result of that collision. And some of that energy of that impact will be transferred to the motions of the atoms within the molecules, rather than those two molecules simply colliding and bouncing off each other as though they were perfectly elastic versions of billiard balls or snooker balls. So there are limitations with the kinetic theory of matter, but in fact we find that it actually is very powerful in making predictions about the behavior of real substances, to the point where we can allow for those simplifications, because the simplifications themselves lead to a very rigorous theory which allows us to predict the behavior of matter in a very useful way. So let's look at the liquid state then. So in liquids, the particles can move more freely than in a solid. They can move translationally, they can rotate, but only within the body of the liquid. And so a liquid has a well-defined surface and a well-defined volume. Now, some particles can escape the surface of the liquid because at any given temperature, some particles will have higher than the average kinetic energy and are able to break free of the forces of attraction, keeping the liquid together. And so this is what leads to evaporation. So evaporation is a change of state that happens at any temperature. And so it is rather unusual in that sense because all other changes of state happen at a constant fixed temperature, as we'll see. So in a liquid, the particles are just about the same distance apart as they were in a solid, perhaps a little bit further apart just due to random motion. But due to the random motion, you sometimes get these significant gaps appearing within the structure of the liquid. But on average, they're very, very close together. And so typically liquids are, again, difficult to compress, and this leads to us being able to use liquids as a means of producing hydraulic machines, for example. So liquids are difficult to compress, they can flow to take the shape of their container because the liquid's particles are free to move. This is because the particles are moving with sufficient energy to overcome the forces of attraction between them enough to move translationally. So when we heat a liquid, then we again are raising the average kinetic energies of the particles of the liquid, and so therefore we will increase the rate of evaporation because more of those particles will have sufficient kinetic energy to break free of the forces of attraction between them at the surface and enter the gas phase. So this is again a very simplistic model of the particles of a liquid. So if we look at a gas, in the gas state, the particles are moving much more rapidly and they are much more widely spaced apart. Now, it's important to remember here that in between the particles of a gas is complete vacuum. So they move rapidly, they undergo frequent collisions with the walls of their container and with each other. So a gas will spread out to occupy the full volume of its container, because the particles have sufficient kinetic energy to fully overcome the forces of attraction that existed in the liquid phase. So a gas will occupy the whole space of its container. Now, the collisions between gas molecules and the walls of their container are what is responsible for the phenomenon of gas pressure. As the temperature of the gas increases, the collisions between the gas molecules and the walls of their container become more frequent, and therefore the impulse, the tiny force imparted by each one of these collisions to the walls of the container results in a greater amount of force being exerted at any given time on the walls of the container, and therefore a greater gas pressure. So gases like this diatomic gas here, as you can see, these molecules are diatomic molecules like oxygen or nitrogen. We can see here that the particles are moving freely, translationally, rapidly, and they are colliding frequently with each other and with the walls of their container. So when we compare the three states of matter, we see these relative comparisons. Now, it's important to note here that there is the phenomenon of diffusion. Now, diffusion refers to the random motion of particles from a region where they're in high concentration to a region where they're in lower concentration. And this happens purely as a result of random motion. So if I increase the number of particles in the left-hand side of this box to the left of this partition, and then I suddenly remove the partition, the random motion of these particles will mean that on average, more particles are moving to the right than there are to the left. There are some moving to the left, but the net motion is to the right. Now, if we compare diffusion in a gas to diffusion in a liquid, in a gas it happens more rapidly simply because of the more rapid movement of particles and the fact that they have more kinetic energy with which to overcome the forces of attraction between them. So the phenomenon of diffusion happens in both liquids and in gases because in liquids and gases, the particles are able to move translationally in straight lines, whereas in a solid the particles are only able to vibrate, and therefore diffusion doesn't happen in solids. So gases typically have a low density. Now the reason for this is that, again, density is defined as the mass per unit of volume. So if we had to give a numerical definition of mass density, we can define density as being the mass divided by the volume. And so if in a gas you have more particles per unit of volume, you will have, or rather if in a solid you have more particles per unit of volume, you will have a higher density. Liquids, the particles are slightly further spread apart than in the solid, and so they will have, generally speaking, not always, but generally speaking, they will have a lower density than the solid of that same substance. But gases, there are relatively few particles per cubic or per unit of volume, and so typically they will have a lower density. Consequently, gases will typically rise in bubbles through a liquid. So liquids are medium in density, typically between the gas and the solid state of the same substance, and so typically liquids will rise above their solid and solids will sink within liquids. Solids are high in density and will usually sink below their liquids, but there is one common solid that floats on water. And so hopefully none of you should have any trouble knowing which one this is. It is in fact or rather, I think I've given it away. It is in fact water. So in water, water is unusual for a number of different reasons among liquids, in the sense that the solid state of water is actually less dense than its liquid. Now this is unusual, and the reason for this is because of the very special type of intermolecular forces that operate within water. In water, the particles are arranged in a particular way which reflects their geometry. So if we take a look at a water molecule again here, we can see that in terms of its atoms, so if I remove the lone pairs of electrons, the water molecules have this V or bent shape. So the molecule geometry is referred to as being bent. But if we show these lone pairs, these non-bonding pairs of electrons on the oxygen atom here, we can see here that the overall shape of the water molecule is in fact tetrahedral with respect to the positions of these lone pairs. Now it's called tetrahedral because if you were to draw lines connecting the lone pairs and the water molecule, you would end up with a four-sided shape with equilateral triangular sides called a tetrahedron. So in the same way that you have a carbon atom which has two bonds like this, one bond coming out at you like this, and another bond going behind the plane of the page like this, this is called a tetrahedral geometry. Now this is tetrahedral with respect to the bonds. So if we were to join these atoms with each other, we see we have one triangular side, we have another triangular side here, and we have a third triangular side on the bottom and one on the back here. So this is a tetrahedral geometry. Now a water molecule is also, with respect to the bonds and the non-bonding pairs, also tetrahedral. So we have an oxygen, we have one bond to a hydrogen here, we have one lone pair here. So this is a pair of electrons on the oxygen atom which is not involved in bonding, and it sits in a cloud that looks like this. We have another non-bonding pair here, lone pair of electrons, and we have the other hydrogen here. So the geometry here is tetrahedral. Now the way that water molecules will pack in 3 dimensions is by means of hydrogen bonds. So what you'll have is you'll have water molecules with their lone pairs like this and their hydrogen atoms like this. Now, because oxygen pulls electrons towards it much more effectively than hydrogen, we say that it is more electronegative. These pairs, these bonding pairs of electrons, are not equally shared between the oxygen and the hydrogen. And so these ends, this end of each one of these bonds, the hydrogen end, is slightly positive with respect to the oxygen end, because this pair of electrons is pulled towards the oxygen atom. And so this end is also delta plus, slightly positive. We use the Greek symbol delta to mean slightly positive. So there's an electrostatic dipole across these bonds, which leaves this end of the water molecule slightly negative. And so what happens is the slightly positive hydrogens on one water molecule will be attracted to the lone pairs, these regions of negative charge on an adjacent water molecule. And this happens all the way through solid water. And so in solid water, this tetrahedral arrangement of hydrogen bonds around these water molecules in 3 dimensions leads to the solid state of water actually being less dense. These molecules are further apart than they otherwise would be if you didn't have this tetrahedral arrangement of hydrogen bonding within water molecules. And so water is unusual for many different reasons, but one of the reasons it's unusual amongst other liquids is that the solid state of water floats in the liquid, and this is because the solid is less dense than the liquid. Now, this is very important for life on Earth, because otherwise water ice would sink to the bottom of the oceans, and at least in the northern and southern regions of the Earth, essentially the oceans would freeze solid from beneath up to the surface. So this is one of the many unusual properties of water, and it's a consequence of the particular type of intermolecular forces between the water molecules. Now, I mentioned this because in the Q&A discussion in one of the previous lessons of this topic, I went into detail with a number of the students who had asked about the various kinds of intermolecular forces. And I mentioned that hydrogen bonding is incredibly important. It is the strongest of the 3 main kinds of intermolecular forces. And it's incredibly important, not just in the properties of water, but in that it is largely responsible for the shape and therefore for the functions of biological molecules like DNA and proteins, for example. So we've mentioned that temperature can be measured operationally by means of temperature scales. Now, the problem with temperature scales as a measure of temperature, as a measure of hotness or coldness, is that one temperature scale might measure temperature in a particular way, and another temperature scale might measure it in a completely different way. Temperature scales are developed in accordance with physical phenomena, which will vary in accordance with temperature. So, for example, the Celsius scale was based upon the temperature at which water would melt and the temperature at which water would boil. And they were arbitrarily given those values of 0 degrees centigrade and 100 degrees centigrade. In fact, it was actually the other way around originally, but it was reversed. And so originally, the temperature at which water melted was given the number 100, and the temperature at which water boiled was given the number 0. It was then reversed. But that was based upon a thermometric variable, a variable which changes in relation to temperature. And so many thermometers, like this one, for example, are based upon the expansion of a liquid as its temperature rises. That is the thermometric variable that this thermometer is based upon. But this doesn't really tell us what temperature is. It just gives us a way of measuring it. So what we're doing here is we're defining temperature in terms of a chosen scale of hotness or coldness. But what about if some other scientist came along with, let's say, the Fahrenheit scale? Are they wrong? Are they better? Is that a better scale than Celsius or not? So instead, we as scientists more rigorously define temperature as the average, as a measure of the average kinetic energies of the particles of the substance, and we use the Kelvin scale or the absolute scale of temperature as a standard unit of temperature, because on the Kelvin scale, absolute 0 Kelvin corresponds to the temperature at which all particle motion completely stops. And so the Kelvin scale of temperature is called the absolute scale of temperature because it represents a way of measuring temperature which corresponds with our theoretical definition of temperature. If temperature actually is a measure of the average kinetic energies of the particles of a substance, then obviously you can't have a lower temperature than 0, because at 0 the temperature, the motion of particles completely stops. So this is what we mean by temperature. So we can use many different temperature scales, but it's the Kelvin scale which is the absolute measure of temperature. So heat is something that I mentioned before. It's the transfer of internal energy from higher temperature to lower temperature, and this is in fact the way that we define. This is actually this is actually where we get the theoretical definitions of thermodynamics from. So we measure, because it's a measure of, because heat is a measure of the transfer of energy, like any form of measurement of energy, we would give the units of heat in the same units that we measure energy in, which is in joules. So when we heat an object, heating is the process of adding heat energy to an object at a greater rate than the rate at which the object loses heat energy. So the temperature of an object will rise above that of its surroundings. Now this is very important, and this is another one of those kind of common misconceptions. When the temperature of an object is rising, so if we have, let's say, or let's start with a hot object actually, since I'm using the red color. So if this object is hot, in other words, it's at a higher temperature than its surroundings, some people would consider the direction of heat flow to be outwards from this object to the surroundings. Now in that, they would be half right. It's not just that the fact that the temperature of the object is higher than that of its surroundings and therefore heat will flow outwards. It is the net flow of heat that is outwards, because there is also a lesser movement of heat into the object. So heat moves in both directions, but the average motion, the net movement of heat, is from the hotter object to the colder object, or to the cooler surroundings. Now if we compare this to a cold object, an object which is at a lower temperature than its surroundings, then the net movement of heat is into the object from its surroundings. But that doesn't mean that that's the only direction that the heat moves in. So heating and cooling involve the net movement of heat, the net movement of internal energy in one direction or the other. So a cold object will radiate some heat into the surroundings, but it will absorb far more from its surroundings than it radiates. So this is how we kind of conceptualize heating and cooling. It's important to remember that the direction of heat energy transfer is not unidirectional under any circumstances, but the net direction of energy transfer is outwards from a hot object and inwards to a cold object. So cooling, therefore, is the process of losing heat energy at a greater rate than it's being taken up. So the temperature of the object will therefore fall below that of its surroundings. Now, if an object is being heated or cooled, then its temperature will rise or fall. So if we imagine, for example, let me just bring up my whiteboard here again. In fact, let me start another document here. There we go. Okay, so let's imagine we start with a piece of solid material. So let me turn my pointer off because that's starting to annoy me. Okay, so let's say we start with a piece of solid material and we start heating it. And let's say we plot the temperature of that material. We record the temperature of that material as time progresses and we continually heat it. And then we plot our results on a graph. So let's say we end up plotting a graph of temperature on the vertical axis and time on the horizontal axis. So at time equals 0, we start heating. And we continuously heat that all the way through the experiment. So this is our temperature, let's say in Kelvin, and this is our time in seconds. So let's say we start at a particular temperature and we start heating it. Well, we are transferring thermal energy to that object on average. The net transfer is to the object, and so as we would expect, its particles move more rapidly and its temperature will start to rise. Like this. So during this phase, and again we're dealing with a solid material, its temperature is rising. Now we could just as easily have started with a liquid or a gas, but let's just say we're starting to heat a solid. Its temperature will rise. Now during heating or cooling, we can calculate the amount of heat energy necessary to raise the temperature of an object by a certain amount of degrees centigrade by means of a value that we call the specific heat capacity of that material. So every material, every element, every compound will have its own unique specific heat capacity. So if we take, for example, let's say iron. So if we take iron and look at its physical properties, let's see if we can find its specific heat capacity. So its molar heat capacity, which is another way of measuring the same idea, is that it requires 25.1 joules per mole of iron to raise its temperature by 1 degree Kelvin. So we see here that iron requires a certain amount of energy in joules to be supplied to it, heat energy to be supplied to it, to raise the temperature of 1 mole of iron particles by 1 degree Kelvin. So specific heat capacity is an equivalent concept. It's the amount of heat energy transferred when a unit mass of a material, 1 kilogram, changes its temperature by 1 degree centigrade, and you can also say by 1 degrees Kelvin, because an increase or decrease of 1 degree centigrade is the same as an increase or decrease of 1 degree Kelvin. The increments of those two scales are the same size in terms of changes of temperature. So let's demonstrate this by means of a very simple analogy here. So let's imagine we take a pastry from the oven. So we've just been baking this pastry in an oven. When we do this, the filling inside the pie will stay hotter than the pastry which surrounds that filling. Now the reason for this is because the specific heat capacity of the filling is higher than that of the pastry. So the specific heat capacity of a material, you can think of it in a very basic way as being a measure of the energy needed to increase the temperature of 1 kilogram of that material by 1 degree centigrade. It's also specific to that material. It is unique to that material. This is why we call it the specific heat capacity. So the units of specific heat capacity are joules per kilogram degree centigrade or joules per kilogram Kelvin. So the rate at which a substance transfers heat can be calculated using a formula which includes the specific heat capacity of the material. So the heat energy transferred. Now this also applies to cooling. If you take a certain amount of heat energy away from the material, its temperature will fall in accordance with the amount of material that you've got in kilograms and its specific heat capacity in joules per kilogram degree centigrade. And the formula that connects these is this one. So E here is the heat energy transfer, the heat energy change that has occurred. If you're increasing it, the heat energy, increasing the temperature, the heat energy transfer will be to the object. If you're decreasing its temperature, the heat energy transfer will be from the object. So E is measured in joules, M is measured in the standard units of mass, which would be kilograms, and the temperature change is measured in degrees centigrade or degrees Kelvin. So, for example, the specific heat capacity of water is 4,200 joules per kilogram degree centigrade. So this tells us that we need 4,200 joules of heat energy to be transferred to 1 kilogram of water to raise its temperature by 1 degree centigrade. So specific heat capacity is a physical property of the material itself. So let's start with, let's try a basic example. So calculate the heat energy transferred when a large bath of water with a mass of 900 kilograms cools down from 40 degrees centigrade to 20 degrees centigrade, given that the specific heat capacity of water is 4,200 joules per kilogram degree centigrade. So I'm going to pause here and let the students that I have in attendance with me see if they can calculate the answer to this question. So how much heat energy would be transferred from that large bath of water as it cools from 40 degrees centigrade to 20 degrees centigrade? All right, very good. So let's have a look at how we do this. Now, this one's fairly straightforward. So the first thing that we need to do is to look at the temperature change. So we've gone from 40 to 20. So the temperature difference is 20 degrees centigrade. We have the mass of water, 900 kilograms. We have the specific heat capacity. So we can simply substitute those values into that equation. And we get 75,600,000 joules. So this is 75,600 kilojoules. So this is a huge amount of energy. This is approximately enough energy to run a computer for about 9 days. So this not only shows us the enormously high specific heat capacity of water, it also tells us why it's more economical to have a shower rather than a bath on average. So again, we've just used this formula. The energy transferred is the mass times the specific heat capacity times the temperature change. Now, if we knew how long it took, we could simply divide this energy transfer by the time taken, and this would give us the rate of heat energy transfer in watts. Now, heating or cooling involves an increase or decrease in temperature, at which point we would use this equation to understand what's going on in terms of the specific heat capacity of the material and the mass of the material that we're dealing with and the temperature change involved to calculate the heat energy transferred. But heating and cooling doesn't always lead to a rise or a fall in temperature. So let's take a look back at the whiteboard here so I can demonstrate. So we've just heated our solid, its temperature rises, but at some point we are going to reach a temperature which is characteristic of that material, which is called the melting point temperature. Now at this point, if we continue heating, then the object will melt, the solid will melt. Now what's interesting is that melting happens at a constant temperature. So while that solid is melting to form a liquid, the temperature stays constant at that melting point, despite the fact that we're continually heating throughout that entire period of time. So at this point, so between this point in time and this point in time, so this is where melting is taking place. Now we are heating the solid all the way through this period of time, but its temperature is not rising. Something else is happening to that energy. Now energy is conserved, it's not created, it's not destroyed. So clearly the energy must be going somewhere. We are heating the solid continually, but its temperature isn't rising. So what's happening here? Well, what's happening is that the heat energy is not being used to increase the average rate of motion of the particles. It is being used to cause a change in phase, a change of state of the substance. So let's have a look at how that works. So as we heat, we can turn a solid to a liquid at its melting point, and this happens at a constant temperature. Now, the thing to remember here is that when we heat a liquid to a gas, it's not the same as evaporation. Evaporation happens at any temperature for a liquid, any temperature above absolute zero. Liquids at all temperatures will evaporate. The higher the temperature, the greater the rate of evaporation. But when you reach the boiling point of a liquid, something else is happening. It's not evaporating, it's boiling, and there is a difference. So boiling, like melting, happens at a constant temperature. So as we heat, we get melting, and as we boil, when we hit the boiling point, we get boiling. Now, so if we look at our diagram here, we've now got a liquid. Let's say the whole liquid the solid has melted. We now have a liquid. So now that we have a liquid, we continue to heat, and the temperature of the liquid will rise again. But then we're going to eventually hit the boiling point temperature of that liquid. Now at this point, any further heating that we do is going to boil the liquid, and unlike evaporation, boiling also happens at a constant temperature, even though you're continually heating that liquid. So here is our boiling point, and boiling, like melting, is a change of state, a change of phase that happens at a constant temperature, which is unique to that substance that we call the boiling point temperature. So this is boiling taking place. So here we have a liquid which we're heating and its temperature is rising. Here we have boiling taking place, and once all the liquid has boiled and become a gas, any further heating will simply raise the temperature of that gas. Now there are other states of matter which we could get to, like plasmas and Bose-Einstein condensates and thermionic condensates and all sorts of other high weirdness, but at least at GCSE level we'll restrict ourselves to the three more common states of matter, or rather not more common, because in fact most of the mass of the universe is actually in the plasma phase, but the more familiar states of matter, I should say. So this is what we would describe as a heating curve, and as we'll see, as we can see, when you have a solid or a liquid or a gas and you are increasing its thermal energy by heating it, by transferring internal energy to it in the form of heat, its temperature will rise, and it's under these circumstances that you would use the equation that we saw earlier for specific heat capacity to understand what's going on. But during these phases, melting and boiling, which happen at a constant temperature despite heating, that heat energy is not being used to raise its temperature, and so we can't use that equation to understand it. Now, equally, if we go in the opposite direction, let's say we started here with a gas and we cooled the gas down, well, we're taking thermal energy away from the gas, and so its temperature will fall. But once it reaches the same temperature as before, the boiling point, which we would now call the condensation point, the gas will condense to form a liquid. Now this also happens at a constant temperature. So if we're going in the opposite direction, once we hit the condensation point, we call it the condensation point because that's what's happening, but it's the same temperature as the boiling point. Once we cool a gas down to this temperature, if we continue to cool it, we're continuing to take thermal energy away from it. Its temperature will remain constant while it condenses. And then once we've got a liquid, we start to cool the liquid down, its temperature will decrease, and then it hits the freezing point. It's the same temperature as the melting point. We call it the freezing point because we're going in the opposite direction. We're freezing it rather than melting it. And again, freezing happens at a constant temperature while you cool the liquid, while you take thermal energy away from it. And then eventually you will have a solid, and then you can cool the solid down and its temperature will decrease. So how do we understand this then? Well, if we're boiling water in a beaker with a Bunsen burner, we're supplying heat energy to it, but while it boils, its temperature doesn't change. So this means that even if you were to put a second or a third or a fourth Bunsen burner underneath the beaker while it's boiling, and you put a thermometer in there, the thermometer would still read 100 degrees centigrade, and it would stay at 100 degrees centigrade while the liquid was boiling. So clearly something is happening to that heat energy which doesn't involve increasing the average kinetic energies of the particles of the substance. And so we can actually do this in the laboratory. If we start to heat a beaker of water, its temperature will start to rise. So if we time this, its temperature will rise until eventually it hits the boiling point. Now once it hits the boiling point, we're continually heating it, but its temperature isn't rising. So what's happening to that heat energy? This is what we call latent heat. Latent heat, the word latent means hidden. So if we were to heat ice as well, if we were to heat water ice, we would see a similar thing. Its temperature would stay at zero until all of the ice had melted to become a liquid. Once you heat that liquid to 100 degrees centigrade, it would stay at 100 degrees centigrade despite further heating. So where does the energy go? Well, the energy is going to increase the rate. So if in the case of a liquid, the energy is going to essentially into overcoming the forces restraining the water molecules and keeping them stuck together. We are doing work against the heat energy change. The heat energy transfer is being used not to increase the average kinetic energies of the particles. The temperature remains constant. That latent heat energy, which isn't showing up as a rise in temperature, is being used to overcome the forces of attraction between the liquid, the water molecules, in order to turn them into a gas. So the amount of energy which is transferred during the change of state of a substance without a change in temperature is referred to as the specific latent heat of that substance. So when a kettle is used to boil water, the electrical energy is used to convert the water from a liquid into steam. So the specific latent heat of a material is a measure of how much energy it needs to change state, for example, to melt or to boil at a constant temperature when you have 1 kilogram of that substance changing state. And like specific heat capacity, specific latent heat is also unique to each material. It is specific to that material. Now, in this case, we're simply measuring the amount of energy to change the state of 1 kilogram of material at a constant temperature. So unlike the previous units, you don't need units of temperature. The units of specific latent heat are simply joules per kilogram. How many joules does it take to change the physical state of that material from, for example, solid to liquid if you have 1 kilogram of that material? So the specific latent heat of fusion is what we this is the term that we use to refer to the energy needed to change the state of a substance between solid or liquid. Now, it's the same term used in both directions. So the specific latent heat of vaporization is the term used to describe the energy needed to change 1 kilogram of a substance between the liquid state and the gaseous state. Now, whichever direction the change takes place, the specific latent heat is referred to using the same terms. It's just the sign before the value for the specific latent heat changes from positive to negative. So when you're going from solid to liquid, you're melting at a constant temperature. It is the specific latent heat of fusion, and that value is positive because you are supplying energy to that system. If you're going from liquid to solid and you're freezing 1 kilogram of a liquid to form 1 kilogram of a solid, then it is the same value, the specific latent heat of fusion, but the value is negative because you are taking energy away from that system. So, to give you some examples here, the specific latent heat of fusion of cast iron is 100 kilojoules per kilogram. So cast iron will melt at this temperature once you supply 100,000 joules per kilogram of cast iron. Aluminium has a melting point of 660 degrees centigrade and has a specific latent heat of fusion of 321 kilojoules per kilogram. Now, the amount of heat energy transferred into or out of the material undergoing a change of state at constant temperature can be calculated using a different formula. So this formula is this: the energy transferred during a change of state is equal to the mass of material in kilograms multiplied by the specific latent heat of that material for that change of state. So if you needed one of these formula triangles to rearrange, then you could use this one. So energy transferred is the mass times the specific latent heat. To get the mass, we divide both sides by the specific latent heat, and we get this: mass is equal to the energy transferred divided by the specific latent heat. To get the specific latent heat, we divide both sides by mass, and we get this. So here's another one for you guys to try. So calculate the energy transferred when 2 kilograms of water boils at 100 degrees centigrade, given that the specific latent heat of vaporization of water is 2,272,000 joules per kilogram. So I'm going to pause here and let you guys have a go at this for yourselves. Okay, very good. Yeah, so it's a pretty straightforward problem here. So you would need this equation. You simply substitute both our values in because we have them both in standard units. We evaluate and we get 4 0.544 million joules, or 4,544 kilojoules. So this is a fairly straightforward problem, and there are going to be a number of other problems that I'm going to be working through with the students that I have in attendance. But for now, thank you for watching. I hope that was useful, and I'll see you on the next one. Take care.